Welcome back for the last day of our summer school. The first lecture is given by the...
Okay. Yeah, good to see you all here after a fun evening last night. So far as I could tell, Brazil scored 4 goals, but made things even by scoring 1 in their own net. Yeah. Okay, so today we begin by moving into an area that I'm less familiar with. But it's the real motivation for the G2 structures I was talking about in the last lecture. So G2 is an exceptional Lie group, and in dimension 7 you can create manifolds whose holonomy lies in G2. So in G2, the automorphisms of Octonians, and it's canonically embedded in SO7 and also in spin 7. So in G now is going to be a Riemannian manifold with holonomy G, and remember that is the subgroup generated by parallel transport around all paths. So, I mean, if you're interested in, the hard thing is full holonomy. If you just want a subgroup, then any flat manifold will do. Okay, then the holonomy is trivial, so that's good. Or maybe you would take a Calabi-Gow, in which case the holonomy of G would be SU3, and then you would take n cross S1, a flat metric on S1, and S1, and here the holonomy is also SU3. SU3, actually it's nice once again, G2 acts transitively on here on SO on the 6th sphere, so in fact smooth fiber model. So what you will notice about the fundamental groups of these examples is that they're infinite. And in fact, that's a theorem of Joyce I'll state later on. If you have holonomy G2, you get the whole group, it's full holonomy G2, if and only if the fundamental group is finite. So that's the hard thing to build. But before I tell you a little bit about G2 geography, now I want to tell you about the free form. This is an alternative definition of G2 structures. And it will turn out that from this point of view, from a G2 structure built by a 3-form, you can make a metric, and then you just need the 3-form to have special properties. So this is just basic. The first 15 minutes of this talk will be basics of G2 geometry, which is more in the line of general education for people who are interested in the subject. So here are the imaginary octonians, which we can identify with R7. And maybe you remember, one of my favourite parts of high school mathematics, I think it was my final year of high school, when you did the vector cross product, the vector triple products, when you computed volumes of things with vector triple products. And I don't know, maybe you thought you were doing something rather general, but that's actually a very special feature. That cross product is related to the multiplication in the quaternions. And in a similar way, you get a vector cross product on the imaginary octonions using the division algebra structure here. So this allows you to define a 3-form in the following way. Given 3 vectors, you just do what you did at high school. You take the cross product of the first 2, and then you take its norm of the third. And this is extremely beautiful natural 3-form. So this is called, this guy here is the canonical positive. And here is another amazing fact, which I think I can just put in here. If you actually look at the automorphism group of this 3 form inside of all of GL 7, that is actually another characterization of G2. So this is the, stabilizer. Okay, so one of the things I said last time was a beautiful way to think about a G2 structure. So let's take this global G2 structure. Each tangent plane, with the imaginary Hamiltonians, so you get this 3 form. So positive 3 form and phi it's a 3 form to phi x. So now you can, and because, so a G2 structure will give you a global positive 3 form, because G2 is precisely the stabilizer. Conversely, if you have a global 3 form, you get a G2 structure, much as we got a G2 structure from a spinor. Now,
sorry, what does positive mean for a 3 form?
I'm getting to that now. There's a way to construct a metric from such a 3 form, and I'll just sketch how you do that. And the point is, from such 3 forms, you get non-degenerate metrics. So that's where the word positive comes from. Phi will give you a metric. The first stage of this is easy, and I will skip the hard part. So the metric is G sub phi. You take 2 vectors. Well, what have I got? I've got a 3 form, so I can contract along the vectors, okay? So I can contract my 3 form with 1 vector. I can contract with another vector. That's 2 forms, but I have my original 3 form, okay? And now, if I had a global volume form, I can compare this, okay? And then there's an extra round of thinking you need to do to actually, at the moment this is some sort of conformal classing metric, but you can actually make this strict and get a metric. So being positive is precisely this equivalent to this metric being non-degenerate. Okay, so with more work. Phi positive. And so now I have a metric, and I can ask, does it have holonomy G2? And this is the theorem of Joyce, and then for the second part, Fernandez. Correct. And they'll say exactly when this is true. So this has holonomy G5 inside of G2. Only if phi is apparently trivial under the derivative associated to phi, and then this is if and only if d phi equals 0 equals d star phi. This sort of looks surprising, this equation, surprisingly simple until you realize that the star is given by the metric. So this is a set of linear DEs, but the complication comes in because phi is involved in the definition of the star. So you get,
It's non-linear.
sorry?
It's non-linear. And the star does depend somehow on phi linearly, the product does depend quadratically.
Yeah.
And if it were linear, it's non-linear. So the first one doesn't look that linear.
Yeah, okay. I couldn't tell you exactly. So far as I remember, this is an extremely overdetermined set of PDEs. But all right. Sometimes it has a solution. So from this point of view, we need to find the actual moduli space. We can, of course, define it as holonomic geometrics, but it's often nice to think of this in terms of positive 3 of. So that's the positive 3 forms, they satisfy this equation. And now mod out by the action of the spin diffeomorphism. So now we can do, I'm just going to do a little bit of G2 geography and tell you what's known about these sorts of manifolds. And I'll write this as a long theorem. Almost all of the results are due to Joyce, but when they're not, I'll indicate that. So, close holonomy, I'll write this equals G2. So full holonomy manifolds exist. So that's reassuring. And Joyce constructed hundreds of homotopy types.
Only hundreds?
Sorry?
Only hundreds?
Only hundreds. Joyce himself constructed about 100. And he did this, he could compute the Betty numbers. Just look at the list. Of underlying, obviously the underlying matrix. So I said this before, but I'll repeat it since it's a very important fact. So M phi now has holonomy equal to G2. That's if and only. So what I mean here is if M phi has holonomy contained in G2, then you get the full thing, if and only if the fundamental group is finite. So these examples here had proper holonomy G2 and infinite fundamental groups.
Excuse me?
Yes?
The most of these homotopy types non-simply connected?
No, they're mostly simply connected.
Oh, okay.
Yeah, the fundamental groups known, they're not so complicated. So pi 1s that have been constructed, they tend to be simple abelian groups. They're the only two for certain that I know, but I think there's probably Z6 and Z12. But there's no theorem about which pi 1s can arise. But the things are very hard to build. So in terms of the subject suffers at the moment because G2 manifolds could be generic, but there's no way to build them. There's only a finite number of underlying diffeomorphism types constructed. So if you want to conjecture a theorem about G2 manifolds, you don't know because you don't know that we just haven't found enough of them yet to have the right picture.
So it's also not impossible that there are infinitely many homotopy.
It's not impossible that there are infinitely many. Yeah. Here's an important point for our discussion. So this implies if I take this 3 form and I couple it with P of M, that this is negative. And this is a statement in R, so in particular, Q coefficients, R coefficients. So, yeah, absolutely. That tells you, for example, that well, B3M, oops, B3 and B4 is positive. And while I'm here, this space here, so MG2M, well, before we mod out, it's locally isomorphic to the perturbations you can make in the 3-form. So this is an orbifold under okay, so we know the rank, we know the locally the moduli space away from bad points is Euclidean space, and we know its dimension. Here's another thing that Joyce proved.
Or is the diffeomorphism group you're dividing by discrete?
No, it's the full thing. If you mod out by the diffeomorphisms connected to the identity, then you get a manifold. And then the pi naught acts to give the orbifold structure. Here's another thing you can do with the 3-form is you can use it to construct a bilinear form on H2 just by taking some cohomology classes and coupling them with the 3-form. And this is negative definite, given the orientation conventions, but it's definite. Okay, so that's a strong constraint. I mean, if there's no H2, there are 2 connected examples. It doesn't say anything, but if there is H2, then you have this product structure. And now, this is a theorem of Baraglia. So he used Donaldson. Donaldson theory showed that this point here implies that if you have holonomy, full holonomy G2, you can't fiber over a 3-manifold. Okay, well that's all some general statements. What about something explicit? After Joyce, you couldn't point to any particular familiar diffeomorphism type of 7-manifold and say, hey, that's G2. But that's the industry of folks of Corky, Aston, Nordstrom, King. So there exist tens of thousands of two metrics. So I'll talk about their construction. It's the so-called twisted connected sum construction, and I'll talk about that in some detail, at least the topological aspects of it in a moment. But in particular, there is 2 connected examples. So 2 connected examples. And many examples on the same underlying manifold. So that's good. And then you can start to try and prove theorems. You can even now start to wonder if the moduli space could be connected, because you've got 2 G2 metrics constructed in very different ways, and for classification reasons, you know they're on the same underlying manifold. And in terms of the simplest one,
Can you say that again? Didn't you say the orbifold is a quotient of Euclidean space?
it's locally. This is locally. That's a local structure.
Okay.
No, the global structure of the thing is what I'm completely unknown. It's just a local statement. Locally, you can preserve this 3-form by them. Let's say some harmonic forms. The simplest example, So you remember, this is the notation for, we took the we took a certain 3-sphere bundle over the 4-sphere with the vanishing Euler class and first contrarian class, spin characteristic class 2, and now we would take a 52-fold connected sum set, S4. Okay, and this has holonomy. And another thing, if you think about inertia, this thing has a full inertia group. This manifold's got a unique smooth structure. But they also do the following. This also has. And that manifold has 2 smooth structures. So now I want to state 3 questions that I think before the new invariant came along, I don't think there was any idea about how to answer them really. Well, there's been other attempts to construct invariants of G2 manifolds using instantons and trying to generalize Floer homology. These are extremely difficult. There are very clever people working on them, having success, but so far there's nothing concrete you can compute with. So the G2 people tell me before the new invariant came along, the following questions were, or 2 of the following 3 questions were just inaccessible. So do there exist exotic G2 manifolds? So M1, G1, into admitting full holonomy which are homeomorphic but not diffeomorphic. So that would be one sort of idea of a disconnected moduli space. Just go to the underlying topological manifold and see if there are different smooth structures. What about if we're on the same manifold, MG1 and MG2, of course, again, holonomy equals to 2, such that the corresponding new invariants are different. So that, let's say, so this is a statement in the topological moduli space. So once we had the new invariant, we set about trying to disconnect the moduli space with it. But you could even try and do better. You could wonder, the new invariant is pretty coarse, so do we have the same data, which are equal in the topological moduli space, but they're in different components of the honest moduli space. And this is the statement in the space you really care about.
What do you mean topological?
The topological moduli space, yeah, so that was this space of G2 structures I can set up last time. So there's this forgetful map. There's the honest moduli space of G2 structures. A holonomy G2 metric gives you in particular a G2 structure. So that was this space I called G2 bar. So the space of G2 structures modulo the action of the full diffeomorphism, spin diffeomorphism group. And then look at this map on pi naught.
Well, you see in particular your example up there, 101, only has a G2 metric for the smooth structure given by that construction and for the other one.
Yeah, so far that's right. When they constructed it for, let's say, the new invariant is 0 for that guy. They constructed it on that one. Yeah, so these 3 questions are somehow wide open, and most of what I want to do in this talk is explain to you that everything happens. So that's what I'll tell you right now for question 1. Maybe it would be better to number for future reference. 1, 2, 3. And then Goethe and Nordstrom, I'll tell you at least an outline of how they give positive answers to 2 and 3. Yeah, so this is just state this as a theorem. So this guy here, which is not diffeomorphic, so the guy up there has holomorphy. So that was the first example of exotic G2 manifolds. It might even be the first example of exotic manifolds with special holonomy. Not clear. But anyway, just emphasize this. Thanks to all this work we did with the generalized Bills-Coifert invariant, these two manifolds are not diffeomorphic. Okay. Yeah, I'll also try and say a little bit about the proof of that theorem. The proof is simple. They have a big machine, 40 Haskins, Nordstrom, and Puccini, so you just build another one and compute its new invariant. But you need an effective method for computing the new invariant, and then you have to be gifted like Nordstrom at actually tinkering with their machine to build you exactly the manifold you want. Okay, so how do these guys do it? So let me just tell you the topology of these twisted connected sums. So from a topological point of view, these manifolds are rather beautiful. So the input we're going to need is certain 6 manifolds coming from algebraic geometry. So these are, if you know the words, these are Fanos or semi-Fanos, and you blow up a lot of exceptional divisors until you have a Kummer surface, K3 surface, sitting in there with a trivial normal bundle. And what you want, the design feature you want, is that when you cut this guy out, you get to what's called an asymptotically cylindrical Calabi-Yau. So this is, by definition, cut out this divisor. So the picture is you have some manifold and then you have this neck coming out here. This neck looks like, let's say R cross F1 cross your, so this is a picture of U plus minus. So you want a Calabi-Yau metric, and as you go to infinity along the cylinder, you want this to be the product metric, a flat metric here and a Calabi-Yau metric on the K3 surface. So I believe this was Donaldson's idea. So what are we now going to do? Yeah, I'll say a little bit more about the history of this. So let's take 2 of these guys. Remember, Calabi-Yau here, the holonomy group is SU3, and that's good because that's a subgroup of G2. And before we knew the crossing with S1, that was a cheap trick. It didn't build the really interesting guys. But I think Donaldson's insight was, well, let's cross with S1 twice and then do something clever. So let's take B plus cross S1 and glue it over a certain product diffeomorphism. And here on the boundary, we have a copy of K2 plus. This goes, oh, I've written them the other way around, sorry. So this diffeomorphism is a product diffeomorphism, and what it does on the torus factors is interchanges them. And on the Calabi-Yau it's something, so T of xy is equal to yx. So this is just a flip. And if you're good at Van Kampen, I should have said that these input 6 manifolds, these are all simply connected. So you just do Van Kampen now, you have a Z and a Z and you cross them over, and this is simply connected. And, okay, it's got holonomy SU3 on it's got holonomy SU3 on the other, and now you have to play a very delicate game of matching in the net to make sure that things match up. But you can. So if you pay careful attention, the K3 surface is a huge family of automorphisms. This flip that you do plays around with the metric. You have to compensate for that, and you have to work hard to find exactly the right diffeomorphism there, but you can do it. And if you do that, then you end up with one of these G2 structures, which in the first place isn't holonomy G2, but it's close enough. So I'll just say that now. Draw a picture. So this is a long neck construction. So here we have sigma cross T2. Here we have maybe inverse orientations. Take care of this. So these comments. Choose and sigma carefully. Then M has D2 structure. Phi close to the holonomy equals D2. And then there are theorems of Joyce. Joyce's original proof, he proved that if you get close enough, there's a perturbation method, and then you apply this. And that's how you do it. So as a topologist, you could wonder, well, what's the class of 7 manifolds I can build this way? Yeah, as I said, I should say this input, again, is constrained from algebraic geometry. So the finiteness of the construction is coming from the input is finite. And that's, at the end of the day, that's because you to build these things, you need algebraic geometry. So the 6 folds you get are actually the solutions to equations and blow-ups of them, and there's only a finite number of Farnows and weak particles. For some time, my conjecture was, well, you know, if you take the product matching like this, there is in some sense a simplest possible simply connected 7 manifold with some primary set of invariants. And I thought for a while that G2 manifolds might satisfy that, but this theorem with Nordstrom more or less shot that down. Certainly the simplest sort of manifold would not have this exotic sphere coming in. So now I think it's basically wide open. And this, to repeat, this is just one particular construction. It's the most prolific construction of these manifolds, but there might be others. We just don't know.
I mean, do you get 2 connected examples out of this?
Yeah, absolutely. So from this, that's where everything that Corti, Haskins, Nordstrom, and Pacini, in particular, those 2 connectors, so in particular. So let me just report on a slightly, well, we had lots of examples. We had an invariant, and we might disconnect the modulo space, but that was not to be. So if you take any, I'll write it like this. If you take any twisted connected sum, if it's twisted connected sum in structure, you get some 4 all the time. But there are some examples of Joyce where this semi-characteristic, you can just compute the semi-characteristic from the Betti numbers and it's odd. So this is odd. So for a long time this was all of what we knew about. We knew that these 2 numbers were different. That was all we knew. And in terms of, I'll just say a little bit about, just a remark in terms of geography. Up to now, mu of mg, this is holonomy equals g2, this has so far always been congruent to 0 mod 3. But this is one of those things where you don't know whether there's a theorem there, maybe related to triality, or whether this is just an artifact of the constructions. Just don't know.
Okay. So in particular, that holds for the odd number above, or you just don't know?
We don't know. Yeah, because all we're getting out of here, you remember there was this statement that mu modulo 2, mu of m, was congruent to this semi characteristic. So it's only a mod 2 information. And for the Joyce examples, we haven't been able to compute mu. I'll just say a little bit about the I'll just say a little bit about the proof. So the real emphasis of the talks I've been giving is to say, understand 7 manifolds by 8 manifolds. Okay? That's a good thing if you're just working abstractly in the theory, because the theory tells you that the 8 manifolds are there. But now you've built an honest 7 manifold, and no one gives you the co-value. Okay? But let's just schematically think about this. This is going to be a picture of our, this is a twisted connected sum here. So this is M. Sum. And this is something you can do with any twisted double, right? So, and I'm going to use capital F to abbreviate this thing. Now, if you have a diffeomorphism and any twisted double, if you don't like the diffeomorphism, if there's another one you like better, you can sort of play a game. And I want to compare this to, so this is just a general thing you can do. You can build a keyhole. So this is, here are my m's. Now I just, to begin with, I cross it with the integral. Well, that wouldn't work. But what I do here is I split it open. And here I put in a keyhole. And when I split it open, the price I'm going to pay, so I do with F here, I do with F here, so this is going to have to be the magnitude of F inverse. So such a board doesn't always exist. So this is M. And that's just happens. This is a nice technique to have when you want to compute. For example, if you want to compute characteristic numbers or invariants, maybe this thing here is something nice, and maybe you can do something with the magnitudes. So that's just a nice general technique to have. So in this particular game, what we didn't really like was that we flipped the torus factors. I mean, that was very good from the point of view of G2 geometry, but from the point of view of understanding the manifold, we didn't like that. So let's undo that. Well, actually, not quite. So we'll take now, so we're going to use plus minus identity. Yeah, sorry. The flipping was okay. So then you can see that F equals to F little inverse, that's going to be the identity across some sort of rotation. So I think if you work it out, you end up, so the rotation x, y is like this, or the signs in the other factor. But the point is, for us in this particular example, that means this mapping torus is the Kuma plus a 3-dimensional mapping torus on this rotation. And with this guy here, because we're now good with the identity, this is going to be of the form S1 plus a 6-dimensional mapping. So the other good thing about this, and this was Johannes's insights, one of his many insights, was that this guy is good in the sense that you can, there are G2 structures everywhere, but you can put a spin 7 structure on this. So you can extend your spinor field without a 0 over this board. So, okay. new invariant here is 0. New invariant here is 0. So this is coming from the product structure. So, and this whole voidism W is spin 7. So you just have to compute its Euler characteristic and signature. It's a big manifold and you need to use Walls-Moon additivity and the signature, and it's hard work, so eventually it comes out. So that's the, I'm going to call that, that's a sensitive and delicate co-boundary, which pays attention to the G2 structure and algebraic geometry. You don't see it from this picture, but the inputs often are huge. They're coming from algebraic geometry. The cohomology group is big. It's actually hard to compute with. But now let me say a little bit about proof sketch. That this guy here so here, now we don't have to do anything sensitive with spinners, and this is what we call the spin C co-boundary. Because it's spin C, I'll explain what that means in a moment. We'll just do the following very brutal thing. We go back and we take Z plus and we cross it with D2. And here we take Z minus and we cross it with D2. So remember, I'm sitting here, so on the boundary we have Z cross S1, and sitting inside of here we have K3 surface. Remember the K3 cross D2 cross D2, right? And draw that like this. Okay, so that's sitting inside the boundary. Remember the K3 surfaces have trivial normal bundle in here and we cross with D2. And now you can just identify these guys here with a flip. Okay, so here you use F sigma times the flip. And if you check it through, the thing on the boundary, so this is W, boundary W is the end that you want. And actually, maybe in the interest of time, so I'll just say it. So this Eales-Kuiper invariant was redefined by Krepp and Stolz, and they called it the S1 invariant. And they had spin C manifolds in particular are not spin. So that's a bad co-boundary for computing any invariant. However, Krepp and Stolz observed that if you have a spin C situation, you can rectify things. So you can still compute the Eales-Kuiper invariant or its generalization from a spin C co-boundary. So in their paper they had, one has to now adapt their ideas. Let me just say a few things about spin C. So as a Lie group, Z2 is S1, so you let S1 is the, Z2 is acting here as the double cover here, you let it rack by 180-degree rotation. And there exists a spin C characteristic file. You check this characteristic. Which is closed. Spin C manifolds in dimension 8. And then you're back in business, and you use the fact that there's a Dirac operator associated to a spin C structure here, so this gives a Dirac operator of an 8 manifold with an index, and you express the index so it's the same game, etc. So now Nordstrom knows what his target is, and he has to go away and do lots of subtle algebraic geometry, and you find a guy, once you look at the construction, that hits these topological invariants, it's two connected, torsion free, and so on. but you can compute the new invariant and you see the Milnor sphere is hanging off the edge. Okay. So in the remaining 10 minutes, 15 minutes actually, in fact, I'm going to give you lecture 2 in an abbreviated version. So I left out one thing from my G2 geography survey is question. Are G2 manifolds formal in the sense of rational homotopy theory? Holonomy. So simply connected 6 manifolds are formal. Dimension 7 is the first dimension in which simply connected manifolds can be non-formal. They can support massive products. And this was actually an exercise that got handed out. So if you have x, y, and z, h up to 2 of m, you get a massive product of h over 5. And there's some people sort of have a view that special holonomy should lead to formality, and some people are agnostic. But I put that in as a motivating question, and the program that I'm going to outline has a way to approach answering that. Okay. So now let's say something about following class of manifolds. So this is going to be sets of pairs M5. Just a spin manifold, but we're going to prescribe an isomorphism of pi 2 of m with C to the r. So if you wanted to now that you've mastered 2 connected 7 manifolds and you want to dive off into the big brave world of simply connected 7 manifolds, killing the torsion in saying there's no torsion in pi 2 will make life a lot easier for yourself. So this is actually a monoid under what you would call connected sum over 2, and this is over 2 by 2. So here's a nice fact. If you have S2, any map from a 2 sphere into a 7 manifold, well, by general position it's an embedding. If n is spin, the normal bundle is trivial, and in fact it's trivialized because pi 2 of SLO is 0. So just once I prescribe these homotopy class up to isotopy, I've got a unique embedding there. So now if this was happening in M0 and this was happening in M1, I could take their connected sum, right? So I would just cut out this copy here. So this is sometimes called parameterized connected sum, and we can glue it to the other one. And okay, one of the things about the group of homotopy spheres is that it's a group. You take the connected sum, you don't change the homotopy type. Okay? I mean, in general, for manifolds, they've got this nice monoid structure that you don't stay in any world. There's more and more topology. So when you want to go up, it's a good idea to have some sort of connected sum operation over the type. Because if you just do Maya Vietoris on this, we stay in this world. We don't change pi 2. Sort of, here we had 2 copies of z to the r, but we kill it. 1 copy in the middle when we take the connected sum.
So you should do this over the arc anyways, it's not just one instance.
Yeah, that's right. This was an example. I just gave you an example. This was r equals 1. And if you've got more of them, just do it more often. So now we can make a definition. The notation is inspired by Cuvier and Milnor. If we'll just take the group of units in this monoid, and that turns out to be exactly these guys, where h3 of m is 0. It's clear from Maya Vietoris when you make this move that h3 is add. But if you set h3 to be 0, that's good. And so this is in fact, so you can check that this is group of units. In the bottom one.
We have single connected to our
Everything's superconnected. Sorry, yeah, thanks. I didn't, that's what the one was supposed to say. Thanks. So I regard this group here, in this particular little world of topology, this group here is as fundamental as the group of homotopy 7 spheres. This is the group you want to understand. Because this group is acting on your monoid. So now you've got a two-step plan for classification. Compute the group and compute the orbits. It's a reasonable procedure. The orbits hopefully will be identified in terms of primary cosmological data, and now you just have to get your hands dirty here. So, here's a piece of advice to all you young people out here. Don't do what I do, which is, I think, prove an interesting theorem and then fail to publish it for 9 years. But okay, we're still going on this, and hopefully this will see the light of day at some point. But a long while ago I computed this group, so it looks like this. Maybe the details, I'll write it down, the details right now are not so extremely important, I just want to say that it's explicit. So this is, I'll tell you what that f to the r is. I'm going to assume in the interest of time that you know what Whitehead's universal quadratic functor is. And so I'll just make some remarks. Fr is given as follows, it's the cubic part of the expression. So this is choose, this is 3 choose from r plus 2 things, and this is 2 choose from r plus 1 things. So basically, this is cubic, this is quadratic, Whitehead's functor is quadratic, this is the group of homotopy 7 spheres, this is quartic, obviously, and in fact, this is determined, if you rationalize, this determines exactly the massive products. And this is all over, all of these manifolds here have an action of GLRZ, and you would be foolish to forget that. In order to get your nice monoid structure, you had to pick this polarization. So this whole identification, the action is known. So this is a split decomposition, and each of the pieces have their own, in principle, known action of this group. Okay. So I'll tell you one other thing about this group. It's interesting from the point of view of mapping classes. You take the R-fold connected sum of S2 coordinate 4s, then this is a semi-direct product of theta 7 to spin equal to R. Yeah. So these manifolds have a pretty obvious action of GLRZ. You can just take the H2 wherever you want, and dually H4 goes where it has to, and then these are exactly the group of diffeomorphisms. And this fits in with the theta 7 picture, okay? So theta 7 was a group of diffeomorphisms of pseudo-isotopy of the 6th sphere, and this is naturally the manifold you would encounter. So this group, the action of this monoid action is take S2 cross D5, connected sum, embedded in your manifold, cut it out, and glue it back in with one of these diffeomorphisms.
That the S2 was S5?
No, it's 6-dimensional, right? So you're cutting out and regluing. So in fact, yeah, the dimension is correct. Okay. And the next thing here is actually a statement about the orbit space. So theta 7 2 spin R acts on M 7 1 spin R. And now we get to introduce some of our friends from the earlier lectures. The fourth cohomology of M, this quadratic linking family, entry eigenclass wouldn't be without him, and now there's cup 2. So this is the cup product structure. So I think that this is a list of primary invariants. You're going to have to fix the cup product structure. You'll have to fix this linking family of the entry eigenclass. But once you've fixed all of these natural invariants, then you've got your manifold up to the action of this group. So we've actually managed to carry out the program that I suggested of understanding one connected 7 manifolds with pi 2 torsion free in the spin category, compute the group, and compute the orbits. I mean, it's a huge group, and this action is complicated. Sometimes the action will be free, sometimes it will be trivial. There's extremely delicate questions in there. But for any particular manifold, you could carry them out. And I'll just say, when M is equal to boundary W, but this happens over pi 2. So another way to say that is this happens over kz to the R2. So before we just wanted a spin boundary, but now we're fixing pi 2. So to apply our surgery methods, we would want everything to happen over here. So then, Massey products and this is complicated. You actually have to understand the differential algebras as a, it's not a primary operation, okay? This becomes primary in W, so this becomes, so you can compute them, becomes cosmological. So if you know the cohomology ring of W relative to its boundary, you can compute the Massey product structure on M.
Is this a general phenomenon that does come up often?
Yes. I mean, if you want to look at this, there's a paper of Cret and Triantafilou where they sort of look at using the modified surgery method and see its implications in rational homotopy theory. And what they'll be telling you is, oh, hold on. Yeah, you can connect it with their point of view. This is, I think there's something general here. If you want to compute Massey products of certain cohomology classes, if you have a co-boundary over the cohomology classes that you're interested in, then the Massey products should be determined by primary things in the co-boundary. I don't know that that's true, but that to me seems like a good slogan. And I'll just say, remember, I've got it here. This spin C co-boundary, this is over H2. So with this spin C co-boundary, you can compute the Massey product structure on these piston-connected 7 manifolds. And we've been doing that, or rather, basically Johannes has been doing that with a little bit of guidance from me, but so far we didn't come up with a non-formal G2 manifold. But from this point of view, it would sort of be a miracle if G2 manifolds were formed. But now there's at least an effective method for these thousands of examples to go about computing. Okay.